Good morning, everyone. So happy to be here, and thanks for the Sarah for the introduction. Thanks the chairs for the invitation to share some work that I've been doing in collaboration with the whole team. I mentioned here some names. Of course, I have space to mention them all, but the work I'm going to be talking about, so I've been done with Blai Bonet, Dominik Drexler, Stahlberg, and other sort of people from the RLeap team. Okay, so I'm going to start basically, as you know, there is a revolution in AI, okay, for the last few years. So I heard that you have heard about deep learning. So, deep learning actually is a very interesting development. I would say it's a true revolution, okay, to be embraced. So the idea in deep learning is you are learning functions, okay, that map inputs to outputs, and you're learning these boxes, okay? These functions, the structure of these functions normally is fixed in the structure of the neural networks, and what you're learning are the weights, the parameters of these functions, or the weights in these neural networks. So the inputs can be a board configuration in chess, and the output can be a probability distributions of the actions to do, or maybe just the probability of winning. You may have the input and image and get in the output, okay, the bounding boxes for objects, okay, and the location of the different objects and so on. So the idea in all cases, and the big success of deep learning, is that you are mapping sort of learning problem into an optimization problem that basically involves the minimization of some loss function. And this applies both in the supervised setting, in the unsupervised setting, okay, like in the case of reinforcement learning, where you use basically these ideas. So this is a true revolution. So among the ones that I admire, okay, so even though I'm not coming from that side, so I'm a good represent old-fashioned AI, so all that, but I'm going to say basically argue that there is still a lot of relevance, and these tools, okay, these techniques and so on, are to be embraced and to be used and so on. Of course, there are a number of limitations, like the amount of data that you need, okay, so how to get something close to a structured generalization, reuse, so how to reuse the things that you learn, okay, how to get systems, okay, that you can understand what's happening and so on. So, and I always like to bring so the other thread, okay, that we have in AI, okay, also for a number of years, that also can be understood as mapping inputs to outputs. That is normally what we call in AI model-based solvers, okay, in contrast with the model-free learners that I mentioned before, okay, so you are basically, the whole idea about classical planning and classical planners, okay, are boxes of this type, so you input problems, let's say in PDDL, and you get plans in the output, you get a such solver, you get Bayesian networks with different sort of queries, and so on, and the idea that these solvers are pretty generalized, are not tailored to particular domains, okay, but particular type of mathematical structures and tasks. And some of these models are actually pretty impressive and expressive as well. And normally the challenge here is scalability and so on. So a big limitation of this slightly different approach, okay, to AI is that the models must be known, and not only in some cases must be known, they have to be expressed in the right language, okay, in the case of classical planning. So you cannot just do the same sort of techniques if you have a simulator or if you have a problem expressed in PDDL. So in some sense, the language in which these models are expressed, so that matters. So another point, okay, that I think is worth making is that there is a way to understand learners as solvers too, okay? So here at the bottom of the screen, okay, what we have is basically the task being solved, okay, in deep learning. In deep learning, we are trying to reduce learning to optimization problem of a parameter space, and you're trying to minimize, okay, some loss function by playing with the parameters. And I will say that this is not an artifact. So it's a good way to think of deep learning as another type of solver to have okay, in the toolkit that we have. And that's going to be one of the points that I'm going to try to be making. Okay, so another theme that also I would say that these days comes often when discussing about the limitations of deep learning is about this parallel, okay, that has been observed between system 1 and system 2 in this dual accounts of the human mind, okay, sort of pioneered and popularized, okay, by Daniel Kahneman in the book Thinking Fast and Slow. So normally system 1 is fast, intuitive intelligence, is fast, associative, doesn't take effort, doesn't require attention. Those are the things that you can do automatically and so on. And normally we associate this sort of boxes, system 1 boxes, to what you get in a learning system, okay, the result from deep learning. On the other hand, so I was talking about solvers, and solvers have a lot to do with the idea of system 2 intelligence, okay, the idea of deliberation that takes time, takes effort, takes memory, attention, and sometimes these days I also joke that it's no longer in fashion, okay, as everybody is trying to play with your system 1 reactions, okay? But one characteristic of the human mind is that these two processes, or these two modes of intelligence, they are tightly coupled, okay? And this is not the case in AI. So one of the main problems in AI is that we have pretty good learners, we have pretty good solvers, okay? But these two guys do not talk to each other at all, okay? And this is very different to what's going on in the human mind. So I would say one of the main challenges, not just me, okay, so has been saying that, is to get this integration between what we could call system 1 intelligence and system 2 intelligence, okay? There are talks, I think that Joshua Benjo, okay, gave a talk, Nishkai, okay, a couple, 2-3 years ago, and actually the idea is how to do system 2 intelligence in a deep learning setting and so on. And indeed, so if you want to bring these two ideas together, the idea of learning, in particular deep learning and deliberation, okay, planning, reasoning, and so on. So in principle, you can go in two different ways. You can go bottom up, meaning so have these neural network architectures. How can I make them reasoning and plan and so on? And on the other hand is to take what I will sort of describe a more top-down approach, okay? That the main difference is that you have to be very clear, have a good understanding of what you're actually trying to learn before you actually develop the architectures for learning that and so on. And I will try to illustrate this difference between what I will call sort of bottom-up, okay, integration of system 1 and system 2, let's say in a setting of action and planning, and top-down approaches. Okay, this picture, what it shows is one of the benchmarks that people in deep reinforcement learning have been used. Okay, it goes under the name of the mini-grid setting, or also the baby AI, but that's the name of the paper, basically, when this benchmark was introduced. So here you have sort of a very much like appears to be a classical planning problem, okay, that is displayed. So there is an agent, so the agent is this, the red triangle over here, and then there are doors, there are locks, and there are keys, and so on. So you're supposed, in some sense, to go pick up the keys, open doors, open other things, okay, to do the task. So actually very similar to one benchmark that we have in classical planning that is grid, okay? So grid is a pretty old benchmark, it's pretty good, it's very interesting. It's very similar to this one. What is the big difference, however, to the benchmark that people use in deep learning? That here, okay, basically nothing is known. You don't know the objects, you don't know the dynamics of the problem, you don't know anything, don't have it in language. And you get instructions like pick up the gray box that is behind you and then go to the gray box and open the door. Okay, and the idea is that normally you get the systems that are going to be trained and to learn how to ground these instructions, either using model-free methods or model-based methods. In model-based methods in reinforcement learning doesn't mean that the model is given, but rather that you learn the control by learning first the model. So at the end, what you need is a control that will accept the goals and the observations and output the actions, okay, to be done. So basically, there is very, very little prior knowledge, okay, to tackle this problem. So, and this is one of the characteristics of the work in deep learning and deep reinforcement learning, is one thing that you cannot criticize people in deep learning is the lack of ambition, okay? So when you look at this, problem, it says, so you don't know anything, and you're supposed in some sense, actually, not only you're supposed in some sense to solve this problem like a planner, you are supposed to get what we're going to call a general policy that will be able, in some sense, to follow the instructions without having to plan. So in some sense, not only, okay, you have a model, okay, at the end, you don't want to plan. You want some sense of system one reaction that will tell you, okay, how to follow the instructions, okay, when the instructions are given. So you want to generalize the instructions, change other modes. So really a very, very interesting and challenging problem that is well beyond the sort of problems that we have been dealing with. And I have to say, it's good to be challenged in this way, okay, by people that in some sense think that they can address these problems. And actually, one of the interesting observations that they managed to get some interesting and meaningful results, okay? Not out of the box, okay? Sometimes you have to do millions and millions of trials, but at the end, you manage to do something that is meaningful, okay? So this approach is actually doing something meaningful, something well, and so on. And actually, we'll say that my main sort of, let's say, criticism, something that I'm going to elaborate, is the problem is the methodology, okay? The methodology normally in deep learning and deep reinforcement learning is extremely experimental, okay, if not ad hoc. What does it mean? What it means is, okay, that if you want to try to publish, okay, some paper, let's say, in this area, so what you try to have is a system that will going to do better than the last system that was published. So if something sort of published getting 78% coverage, and you go and you have 82, okay, you are happy, okay? But you have no idea of what is being missed, okay? So you do 80% here of coverage, so what about the 20% that are missed? Perhaps you are missing the most interesting parts of the problem, okay? So in a sense, so we are missing, okay, with this extremely experimental approach, so we are missing opportunities for human learning, okay? Because we are doing science, and we are, in some sense, when things fail, are very good opportunities to learning what's going on and how things to be improved and so on. And if you don't get this insight and this understanding about what's happening, in a sense, you are condemned to do some exploration, but not the sort of exploration and exploitation, but human exploration. In some sense, you have to start playing with the architectures and so on, okay, without a clear guidance. Okay? And these, in some sense, are the things that we would like to address. So we want to be able to tackle similar problems, but in a more informed manner, okay, by building a vocabulary to talk about these things. So if the name of the game in AI is about learning and exploiting a structure, okay, we better have a good vocabulary to talk about the structures, okay, that we are after. And in some sense, that's what I'm going to try to talk about next, okay? So the agenda, let's say, in what so we could call top-down representation learning is understand, in some sense, first what needs to be learned, and then understand how to go about learning these things that need to be understood. And eventually, definitely, we want to be able to learn these things, okay, with stochastic gradient descent or some variant, okay, that is a very powerful technique. Okay, some questions that arise from this perspective, okay, when you focus in particular in a setting of actions and planning is, so what are going to be good languages or good representations for encoding general dynamics? Okay, what are languages for representing general policies of the type that are being sought in the problem that I mentioned? To talk about subgoal structure, okay, it has a lot to do with reuse. Okay, so in some sense you want to be able to learn to solve, okay, different types of subgoals. I use this knowledge that you obtain, okay, in order to tackle, okay, new goals, how to build hierarchies, okay, what are the principles. Okay, these things cannot be just addressed experimentally. Okay, and of course, the second issue is how to go about learning these different sort of structures, okay, that we care about. Okay, so here is more or less the plan for the rest of the talk. Okay, so I'm doing well. I keep track of time, Sarah. So relax. Okay, no problem. Okay, so no problem. If I don't finish the talk, so it's not going to be the first time. So, at the end, okay, I hope that I managed to convey some interesting ideas, even if I don't manage to cover up the slides. Okay, so basically the plan for the rest of the talk is going to be like this. Okay, so I'm going to talk a little bit about general policies. Okay, because in learning, okay, so we want to learn something that's going to be general. So in many cases, it makes sense to learn for a particular state space, but normally you care about learning things that will apply to many other state spaces as well, okay? And in principle, so we're going to try to characterize and to learn this type of policies using a symbolic combinatorial approach, okay, that is good because it in some sense forces you to understand certain things. I'm going to come back later, okay, and trying to do exactly the same task in a deep reinforcement learning setting, and it's in some sense good, okay, to have these two parallel approaches, okay, to be able to walk on these two legs, okay. On the one hand, the symbolic approach, on the other hand, so there's deep learning, reinforcement learning approach. Second thing we'll talk about is, can we say something mathematical, something about subgoal structures, okay? So you do pre-training, okay, and in reinforcement learning. What are you supposed to learn from the pre-training, okay? So in a sense, this again is a question that is normally being addressed purely experimentally, okay? So the issue is, can we build a vocabulary to talk about subgoal structures, what sort of decomposition space, and so on. So we'll talk about that too, okay? And normally the structures in such a case that we don't refer to them as general policies, we would call them sketches. And I'll come back to the issue of general policies via deep reinforcement learning. And in particular, so one lesson that I'm going to try to convey at the end, okay, is many of these problems, you do deep learning, you do reinforcement learning with deep learning, okay, and the wall that you hit has nothing to do with deep learning, has nothing to do with reinforcement learning, but it doesn't have anything to do actually with planning. It has to do with good old-fashioned logic, okay? I'm going to try to make the point. So in some sense, if you ignore everything, let's say, that is not deep learning, when you are doing deep learning, okay, you are cutting an arm off, okay, if not more, okay? So it's good in some sense to get a good understanding of certain things. By the way, so I'm going to be talking about all these things in the setting of classical planning, not because I don't think, let's say, stochastic models are not good and so on, because in some sense, a very crisp game. So when you talk about generalization in classical planning, we have a very crisp language, okay, where we make a distinction between the domain and instances. And there is something that is shared, okay, across all the instances of the domain. That may be an infinite collection of instances that you're sharing, in some sense, a vocabulary to talk about states, okay? You have a set of predicates that is fixed as you change the sets of objects, but the set of predicates stay the set, and this is what characterizes the domain in addition to the action schemas. Normally, we're not going to talk about action schemas, but we're going to make use of this idea of fixed set of predicates, okay? When you're doing generalization, so you're supposed to generalize, okay, across instances in the same domain. Okay, so just a couple of sort of clarifications. So there is a lot of work, okay, in lines that are very related to what I'm going to be talking about. Okay, so the idea of general policies, I will say the first one, at least that I'm aware, that talk about these things is Ronnie Cardon in a paper that was very influential for what that we did as many years ago. And so there are many other people, so Sid and Neil Immerman. So we have the father of descriptive complexity as a contributor to this thing, so there's Shlomo as well. So there is Felipe and Sylvie that are here on, and so on. And I highly recommend, okay, if you care about the topics I'm going to mention, okay, just to attend some of the talks. At least I'm probably missing some of the talks, okay, during the conference, but these talks, okay, are in particular related to some of the themes, okay, that I'll talk about in here. Some other things. So when you talk about general policies, you cannot use object names in the policies, because object names depends on the instance, and you want to do something that is general. So the way that you normally extract information from the states is through features, okay? So the word feature is going to appear a lot in what we say. So the features are state functions. So you apply a function to a state and you get some value, okay? So if the feature gives you value true and false, it's a Boolean feature, can be a numerical feature, and so on. And when we talk about learning policies and sketches, it means you're learning the features that go with these policies and sketches at the same time. So I'm not going to be talking too much about goals, okay, because I'm going to make something that is normally in deep learning is also used. So I'm going to copy the goal, okay, in the state. So the state of every problem is going to have, okay, the goal. And to distinguish if the goal is to have PC1 to PCK as a goal, okay, I'm going to extend the state with an atom, okay, with a different predicate, PG, to avoid the confusion that whether this atom is true in the state or whether you want this atom to be made true when you reach the goal. So for every goal, P tuple, okay, I'm going to create a new predicate, PG, okay, we call it the goal predicate that I'm going to put in the state, and the idea is that these atoms tell you in this insert, in this state, okay, so these are the goal atoms that you want to achieve, okay, so basically the states contain the information about the goals that need to be achieved. Okay, another sort of remark, okay, before we're getting started, so the shift to feature space, okay, I find it liberating, okay? So in a sense, if you do planning and you have to get stuck, okay, with the PDDs that are given, okay, there are many things you can not just do, you cannot even think about them, okay, which is a problem, okay? In some sense, you move to feature space, you forget about what was actually given, you get two equivalent representations, you're gonna have the same equivalent features, and to a large extent, okay, the deep learning revolution and deep reinforcement learning revolution, it's about, okay, learning these features, okay? Once that you have the right features, so everything becomes easy. But of course, you need to learn these features as you move. But in some sense, really the game opens up a lot, and suddenly you find yourself that there are whole new lands, okay, to be explored and to be understood. So if you're looking for problems, there are plenty of interesting problems, okay, once that you do this shift, let's say, to feature space. I'm not going to talk much about large language models, okay? We have a good ambassador for that. That is Rao, okay? So the lesson, if you follow Rao, is, okay, so talk to me when you solve the blocks world, okay? Meanwhile, okay, so don't trust, okay, large language models a lot, okay? So, okay, so let's get a bit technical now. Okay, so I'm going to start talking about general policies and learning general policies. By the way, so I'm going to make available the slides with reference, okay, later on, so in case you focus on the presentation, so then you're going to have the slides. So, so the way they're going to represent these policies for now is going to be as rules of this type. Okay, so let's say that we have blocks world. I love the blocks world, okay, and I love the fact that large language models cannot do that, okay, but so let's say that we have the infinite connection of problems where you're trying to clear a block, okay, no matter the number of blocks, no matter the initial configuration of blocks, and so on. So here it's basically a policy that accomplishes this, okay? I don't want to do definitions, semantics, language. I want to prefer to do this by examples. So this is a rule that says if you're not holding a block and the number of blocks above the block that you want to clear is greater than 0, then do any action that will make holding true and that will decrease the number of blocks above X. So this rule is not an action, okay? It's more like an instruction. It's saying if these conditions hold, okay, do any action that will produce these effects, okay? So that will make holding true and will cause a decrease in the number of blocks that is sitting on top of X. Okay, normally in this case, there is going to be a single action, okay, that is going to be done. Okay, it's going to be compatible, okay, with this rule. So the second rule in this policy says if you're holding a block and the number of blocks above X is greater than 0, then do any action that will make the gripper empty again, not holding true again. So again, this is an instruction, okay? It's saying if you're in a state where the conditions on the left hold, and these are features, so H is a Boolean feature, N is a numerical feature, so here it's saying then do any action that will make holding true, okay, from the state where these conditions would satisfy. By the way, can you put, okay, the block that you're picked up again on top of N? You cannot, because in that case, in these rules, so if you're the action that puts it back on top of X, so the N is going to increase in value. And by not mentioning the fact that N changes, so every feature, okay, that is not mentioned on the right-hand side has to keep its value, okay? That's the convention, okay, for writing these rules, okay? By the way, so if there are quick questions, okay, so that you can ask in quickly, okay? 1 or 2 sentences that I can also answer and clarify sort of relatively quickly. Please feel free to interrupt, okay? If it's a question that's more complicated, you need more time to formulate, so I'd prefer if you wait until the end, okay? But in some sense, it's good not to get lost. So here, so these are the features. So here is the policy, and as I mentioned, each of these rules is just basically instructions. So it's saying, do an action that complies with one of the rules, any action, okay? So actually the formal semantics of this policy is that the state transition, going from a state to a successor state, is going to be a transition compatible with the policy described by the rules if in S the conditions on the left-hand side of the rule holds, and the transition from S to S prime, okay, so the features mentioned in the effects change exactly as mentioned in the effects. So if a certain feature has to increase in value, okay, so this transition will make that feature increase in value and so on. Once you have the notion of pi transitions, okay, you have the notion of pi trajectories that are made of these pi transitions, starting in the initial states of an instance. And so the policy is going to solve a collection, okay, potentially infinite collection of problems. In every instance in these collections, all the pi trajectories that start in the initial state end in a goal state, okay? So you can actually prove, okay, that this policy take any problem, okay, in this collection of problems, and this policy is actually going to be correct. Now we are writing it by hand, so soon we'll see how to learn this policy as well. So here is sort of a more subtle policy, okay? So this is another problem I'll talk a little bit about later. So delivery, so there is a grid, there are packages in a grid, and an agent is supposed to pick the packages one by one and deliver them to some target cell, okay? So you can have a general policy for this problem expressed in terms of 4 features, okay? A Boolean feature, that is whether the agent is holding a package, and 3 numerical features that actually stand for distances, okay? The distance to the nearest package, the distance to the target cell, and the number of undelivered packages, okay? So the first rule, okay, that has this form will say, if you're not holding a package and the distance to the closest package is greater than 0, then do any action that will decrease the distance to the nearest package, no matter the effect on whether you're getting farther, okay, from the target destination where the package should go, okay? So in some sense to say that some feature can change in any way, just put a question mark and you're making this feature value a don't care in the transition. All the ones that you don't mention, okay, have to keep their values. So second rule says if you're not holding a package and the distance to the nearest package is 0, then do any action that will produce that you're going to be holding the package, no matter what's the effect, okay, on this other feature, and so on. So you can, again, you can take these 4 rules and prove that these 4 rules will solve any problem in this infinite class of problems, no matter the size of the grids, no matter the initial distribution of the packages, no matter, okay, the number of packages, and so on. It's a general policy, generalized in many different ways. So I know you can actually show it to be correct. Okay, so the question is how to solve this policy. As I mentioned, so this is probably going to tackle in 2 ways. Initially, we tackle it as a symbolic approach, combinatorial approach. We're going to be searching in a finite hypothesis space. Then we're going to try to map this problem into deep learning by using a sort of convenient formulation. And we're going to see in both cases, we're going to try to understand what are the limitations of this approach, okay? Because it's not good enough in some sense to solve the problems, but also to understand the problems you're not going to be able to solve in this way. Okay, so the learning task, okay, for learning this policy, I want out to learn these sets of rules. I want to learn the features and to learn the rules. So here's what is going to be given. So the input is going to be a set of training instance from the collection of problems I'm trying to solve, okay, in delivery. So just give me some instance of delivery, okay, small grids, small number of packages, and so on. And basically, I'm going to try to find the rules and the features, okay, to get the policies that I've shown before. So at the end, so I'm going to take these inputs. I'm going to produce, okay, 2 inputs to my SAT encoding. I'm going to map this problem to SAT, actually not just SAT, but mean SAT. In some sense, we are not looking just for a satisfying assignment to a theory, but going to be looking for the best satisfying assignment. I'm going to define in a second what I'm going to be there. So, but basically, so from the domain predicates, okay, we use a simple description logic that is going to be a subset of what is called C2, that is the logic with two variables. First order logic with two variables, that's the name C2, is a desirable fragment of first order logic. So we're going to produce a feature pool of Boolean features and numerical features, okay, from the domain predicates. And I'm going to have all the state transitions that are possible in this set of instances. That is a finite set of transitions in the training set. From these inputs, I'm going to create a theory, okay, a set of constraints, if you want, in a logical language that eventually normally translates to CNF, or actually these days we're using a tool that is called Klingo, okay, that is sort of higher level SAT, okay, based answer set programming, and we're going to solve this, okay? So once that you get this solution, you're going to be able to read what are the features that are being selected from the pool and what are the rules that make use of these features. And actually, while normally these type of talks, you don't want to get into very much detail because you run the risk that many people are going to lose you, okay? In this case, the formulation is extremely simple, and I want to show there is nothing under the rug, okay? That's all that there is, okay? So actually, in this theory, there are basically these type of variables. You're going to have, for every transition in the training set, in the instance, okay, that you sample, you're going to have whether a transition is good or bad. A good transition is going to be a transition that's going to be compatible with the rule that you're going to get. So it's going to be a transition compatible. Second, okay, for every state, we're going to assign a number. And we're going to use this just as a way to avoid cycles, okay, because we got the policy in some sense not to be cyclic, okay. Actually, if you use an answer set programming approach rather than SAT, there are better ways, okay, to encode a cyclicity. Then you have an atom for selecting the features from the pool, and that's it, okay. So basically, these are the two main variables or atoms they're going to have in the theory, and this is just an auxiliary variable, okay, and so on. So the formulas are actually four axioms. That's all what you need. First, you have to see, in every state that I can reach, there has to be some good transition. So if I get to a point, to a state, and the policy will not select any transition, the policy will not get to the goal. So definitely every state that you reach, okay, some outgoing edge has to represent a good transition. Second is, by doing good transitions, you can never get back to the same state. Okay, so basically you are basically saying, so this policy should not cycle on the training set. Second, third constraint is the transition can never be good. It will take you from a non-dead-end state to a dead-end state from which the goal is not reachable. Okay, again, this is in the training set, so I can compute what are the dead-end states in the training set. And the key constraint is, sometimes we call this D2, is saying basically if there is a transition that is good and another transition that is not good, the features that are selected have to be such that they can distinguish these transitions that are good from the transitions that are bad. So in some sense, you are forced to choose features because you need to be able to tell apart good state transitions from bad state transitions. And here sort of these, the features, again, these disjunctions, they are features from the pool, and normally what you're paying attention is that the changes of this feature F in this transition and in this transition, they have to be different, okay, where basically the feature can go up, can go down, or can keep its value. So from this encoding, actually you can prove if the theory is SAT, if and only if there is a policy over the features in the pool that is going to solve all the instances in the training set. This is not only what you care, that's where the optimization part comes in, okay? We not only just want a policy, we want the simplest policy, the one that involves the cheapest features. By the way, what is the policy here? Okay, it's implicit in the good transitions. You see how the features that are selected change in the good transitions, and these good transitions encode the rules that we had before. So you're going to extract the rules for the good transitions by looking at how the selected features change in these good transitions. And that's what you get the rules, okay? So it's all very simple. They can do experiments. I'm not going to get through the table. I don't even know how much this is readable and so on. But the method, okay, does not guarantee that the policy that you get will generalize, okay, to the whole collection of problems. But actually, in domain by domain, what you can show is that these policies that you get will actually generalize. At the same time, so the theories I have to solve, okay, can be pretty large, although we will see that the limitations are not just scalability. There is an expressive limitation that is also arises here as well. okay? So second element, okay, here is, okay, interesting thing, this language that I introduced to talk about policies, I do a tiny change and I can talk about sub-goal structure, okay? That is something that has been lurking in AI for many years. So in some sense, we always talk about sub-goal structure. The normal sub-goal structure that people talk in planning is normally, so the number of sub-goals achieved. But this is, so in some sense, is very shallow type of substructure. So the point is, you can use exactly the same language that we had before with a slight change in the semantics, okay? Very tiny change in the semantics, and now the rules will talk about sub-goal structure and not talk about policies. So policies will be a specific type of decompositions where all the decomposed problems can be solved in one action, okay? But that's not going to be the case in general. So the semantics of these sketch rules, syntax is the same as for policies. The semantics is going to be, if you're in a state, okay, where the left condition holds, then move to a state S prime, such in the jump from S to S prime, you get the effects mentioned in the consequent of the rule. So in the policy, we say just do any action, okay, that will give me the effects on the right-hand side. In a sketch rule, it's saying just go, move to a state, not necessarily at distance 1, okay, that will give me exactly the same effects. And now I can talk. So every rule is now describing a sub-collection of problems. So this rule is no longer a policy rule, but it's not going to be any action in general that from a state where the number of undelivered packages is greater than 0 will manage in one action to decrease the number of undelivered packages, okay? However, this rule is now describing sub-problems. So the sub-problems of reducing the number of undelivered packages by 1. And you can actually characterize the complexity of this problem. So there is something I'm going to have time to talk about, but basically the sub-problems, okay, that result from these rules, okay, have with 2. What mean with 2 is that there is a genetic algorithm that can solve these sub-problems by expanding the number of nodes that's going to be quadratic in the number of atoms, okay? So this is with 2 decomposition of the problem. So this pair of rules, on the other hand, is with 1 decomposition of the problem, which means that the subproblems, and you can solve them more efficiently, okay, by just having to expand a linear number of nodes, linear number of atoms in the problems. So the subgoal structure here is saying, if you're not holding a package, okay, just do things, not necessarily 1 action. You may have to do many actions until you're holding a package. And if you're holding a package, okay, then move to a state where basically you're delivering this package and decreasing the number of undelivered packages, okay? And you can actually show, okay, that the width of these subproblems and so on. So you are in some sense reducing the width of the given problem that is unbounded. You are reducing it to problems of width 2 or width 1, okay, that can be solved by polynomial algorithms. And actually you can keep going, okay? Actually the general policy that we had before is actually a sketch of width 0. It's a particular type of a sketch where the sub-problems that you get in these rules, they can all be solved in 1 step, okay? So that's actually the definition of policy. So all the sub-problems can be solved in a single step. So this is the idea. There is a notion of termination that is going to be handy and so on, but that's basically the idea of a sketch. So now we have a language to talk about problem structure. That, by the way, is something that, again, if you are doing deep reinforcement learning, you are doing reinforcement learning, so this is a dimension that they care. Normally, how people talk about these things in reinforcement learning, they talk about sparse rewards, they talk about intrinsic rewards, and do a lot of crossing your fingers and these techniques on the other, but they don't have a crisp language, okay, to talk about problem substructure, even though that's what's actually happening, okay, in many of the domains. And actually, by a slight change in the learning formulations, so in work, okay, done with Dominik and Jendrik and so on, so we come up with sort of, again, another sort of SAT-based approach, or symbolic-based approach. In this case, we map it into Klingo, okay, for learning sketches. And one of the things for learning the sketches is that you give us a parameter. I want to learn a sketch of width 2. I want to learn a sketch of width up to 1. Or I want to learn a sketch of width 0. That is basically learning the policy. So that's a parameter of the learning algorithm that actually the learning algorithm maps into an optimization problem, not an optimization problem as in the case of deep learning, but an optimization problem in a combinatorial space, okay, that in this case is solved by Klingo. Okay, and in our work, so we are happy because in some sense there are many threads that we are pursuing during the years, the notion of width, the notion of general policies, QNPs, and so on, that they come together, okay, for addressing this problem. Actually, you can keep pushing with these ideas, and you get now sort of a clear account of hierarchies, okay? So in this problem delivery, so how can I get a hierarchical policy? Actually, hierarchical policy, every rule here is a sketch rule, okay? The first one at the top is a dummy rule. The dummy rule is saying if you're in a non-goal state, just move to a goal state. Not a very particularly useful rule, so it's unbounded width. But for this rule, now I say, so give me a sketch that will decompose these problems into problems of width 2. So this rule, okay, single rule, decomposes these problems into problems of width 2. Now, once I get this collection of problems of width 2, I can keep doing the same thing. I say, okay, give me a sketch, okay, for this collection of problems that will decompose the problems into problems of width 1. So this rule, together with this rule here, decompose the collection of problems here into problems of width 1. Do the same thing here. So I want to decompose these problems into problems of width 0, and what problems, once you get problems of width 0, it means that they can solve in one step, so there is no need, okay, for further decomposition. So now you get this hierarchical policy that actually you can apply by means of a stack, and in some sense has a relatively clear semantic and clear meaning. So you're going down, trying to reduce, okay, the widths of the problem, starting from one width that is unbounded to 2 to 1 up to 0 and so on. So, okay, so finishing now. Okay, really? Okay, no, it's okay, it's okay. So I have, so it's okay, it's okay. So I have, okay, it's good. So, but 5 minutes to 15 down. So 5 minutes, okay, good. So get close. Everything is under control. Okay. Okay, so I want now to go back to deep learning. Okay, so the question is, can I do the same thing in a deep learning setting? That is to map the learning of these sort of policies and even sketches, okay, by using deep learning, unsupervised way, as before. Before was unsupervised, I want to use reinforcement learning. And actually, the idea, okay, so comes from, so before what we did is to deal with theory with a set of features and a set of transitions, and these features were coming from a particular fragment of first-order logic that is very well known to be connected to the sort of features that you can get from GNNs, graph neural networks, okay? There's very interesting body of work, okay? So this work by Pablo Barceló and others, okay, and many other works that establish a tight connection between the features that you can get in C2 and that you can get in GNNs. So the idea would be to represent the policy, okay, with a GNN and choose to avoid getting, okay, a pool of features explicit and get the GNN, okay, to do the features for you. And we're going to learn the weights of the GNN, okay, that will be encoded in the policy, okay, using unsupervised learning, in this case, okay, deep reinforcement learning, where the deep learning is coming from the GNN. Okay, so it was in my plan to skip this slide, okay, but to show that there is some substance, okay, so basically it's going to be the relational GNN that you use, that's what matters. So the point that this is very, very tightly connected to the sort of logical features that we're talking about before for C2, then you get basically a GNN is nothing but a parametric map between the states and feature vectors, okay, each one for each one of the objects. Once that you get this feature vector, that is what is called a readout function, one which you get the value function and you get the policy. I'm not going to get into details, okay, but you can get the GNN, you get the readout, and you get these things. And now you adjust the weights of these GNN and readout functions, okay, using a standard actor critic reinforcement learning algorithm. I'm not going to get to this because this is pretty all by today's standards. This is a slight variation of the algorithm that appears in Rich Sutton and Andy Bartos' reinforcement learning book that I highly recommend, okay, for you to learn, okay, to it. Okay, and I come to this slide that I mentioned in a workshop talk and so on, which I particularly like, okay, so this slide, okay, so you do this thing, and you get a general policy, and first thing to notice that you get coverage and generalization in many cases, under certain conditions and so on. It will not generalize to arbitrary size, okay, but that does not matter. That is 100%. So first lesson is, It's not the case that once you start using deep learning, okay, now all the things become 72% and 70%, okay? You can get things to work almost as well as you do SAT, okay? First thing. Second thing is that in certain cases, things do not work as well. Actually, you get results, okay, that are true failures. In some domains, we don't get good policies. Actually, get very bad policies. But when you get a table like this, okay, so this is a perfect opportunity to understand what's going on, okay? You don't start using another reinforcement learning algorithm. You start changing the architecture. You don't start doing this hacking. No, stop for a second, okay, and think, okay? And actually, there are two problems that are going on here. And these two problems, as I mentioned, nothing to do with deep learning, nothing to do with reinforcement learning, nothing even to do with planning, okay? But I would normally say good old-fashioned logic, but it's actually not so good old-fashioned because it's logic in finite model theory. So this C2 is not the standard first-order logic. And the issue is that you can show that the expressivity, both in the symbolic setting and the GNNs, is not enough, okay? So many features that you need that, okay, cannot be obtained in this way. And the second thing that is seldom discussed in reinforcement learning is if you want a general policy, in many problems you can get a general policy, but you cannot get a general policy that is optimal, okay, that minimizes length of solution. Block's world, okay, Block's world, you get a general policy. We all know general policy for Block's world. Put everything on the table, put things in order from the bottom up. But you cannot get an optimal solution because optimal planning in Block's world, okay, is basically NP hard. The issue is actually you can actually verify, okay, these things. So actually we took the job of addressing these two problems by adding some new predicates to the state and changing slightly what we want to optimize. And these things that are in red, okay, actually become 100% as well. So in some sense, proving that this is actually the limitation. Okay, so probably I have a couple of minutes, okay, to get to 50 minutes if I'm right, okay, and so expressive limitations mean something that's very concrete, okay. Take, okay, this Block's world, okay, beloved Block's world, okay, and this is a state, this is another state. Actually, this state is the goal state. You feed this into a GNN, okay, and the GNN will not be able to distinguish this state with this state, even they both, okay, contain the goal. So the goal is encoded as part of the states. One of the states is a goal state, the other is not. So a GNN will inherently, unless you do some other thing, okay, that in this case the solution is simple, okay, will not be able to distinguish them because it does not look at the name. All we are doing is just swapping, okay, the top logs, so if you want swapping the top, and in some sense you're losing track of the states and the bindings, okay, of the own predicates and so on. Okay, actually a little bit about more, okay, I think that Rotislav in one of the talks later on is going to talk about that. There is another paper, okay, coming and so on. And there is a table, so you can do this analysis and see, okay, using coloring algorithms, and you can see, so do I have enough expressive power in a GNN, okay, to target these problems or not? I'm not going to go through this thing, so there is basically a one column here that matters, but if there are questions, maybe I'll get back to this column. So, wrapping up, okay, so deep learning, deep reinforcement learning, a true revolution is great, should be embraced, nobody should feel threatened, and actually, so one thing that is actually a problem in deep learning is not the technique itself, it's the methodology, okay? If you're just purely experimental, there are many things that need to be understood in order to be addressed, and by doing experiments and improving the numbers, you're not going to get this insight. Okay, so what I've been sort of trying to advocate, okay, for a few years is the idea of trying to tackle similar problems. I don't want to change the problem. I want to be able to deal with the same inputs and development. I just want to change the pipeline, okay, to be able to make sense of structure, okay, in the middle and so on. Okay, so there are many, many potential benefits, okay, of this type of top-down approach, transparency, structure generalization, reuse, and so on. And so I'll finish just showing some of the problems, in some sense, they were trying to address, okay, and some other colleagues are addressing as well. So learning what? Basically, these are the problems that we are sort of dealing. So learning lifted action models. Actually, didn't have a chance to talk about that. So learning general policies, sketches, okay, learning from non-symbolic representation, learning in state spaces that are continuous, okay, non-deterministic, and so on. In some cases, okay, the limitations to be addressed have to do with scalability. In many cases, it's about expressivity, and in other cases, still we don't have a good formulation, okay? And with this, okay, I'll finish here. So thank you.